Hi everyone. We'd like to start with a brief overview of what our MVN BIOMECH product line actually entails. The MVN BIOMECH products were launched at the beginning of February this year, 2015, with an updated version of our MVN Studio software. The software comprises a biomechanical model that's built of 23 segments and provides in real time 22 joint angles, full body kinematics, and center of mass representation. It's built from 17 motion trackers that are worn on the body and actually provides full real-time synchronization with third-party devices and a streaming protocol that will allow you to stream all of our data out of MVN Studio through a UDP protocol to anything that can be used for your own application. We have integration with different software, as you can see here, so that the data can as well be streamed easily into software that you might be using already. If we go a little bit deeper into our real-time streaming protocol, this applies directly to our human-robot interaction field. The streaming protocol, as I mentioned, streams not only the raw data coming from the 17 trackers that are worn on the body, but also the full body calibrated kinematic data, the joint angles, and all of the other data that we collect. This data, like I said, can be streamed over a UDP protocol on the computer that you're working on or to any other computer in any operating system that you would want to work in. It applies to both our MVN BIOMECH product line and also even our single sensor MTWs. The last slide I want to show you before we pass things off are a few customer applications that have been done in the human-robot interaction field using our MVN BIOMECH products. The two examples that you see on the left, here and here, were done by a customer using the MVN BIOMECH to control movements of a robot based on specific movements of the body. A movement of the arm could easily move the robot forward or backwards, allow a turn, or allow changing in the software. In the center and in the lower right, you see applications where direct movement of the human body is mapped to a humanoid robot. These applications are quite easy to use because it allows full body movement to control exactly what a robot would be doing as well. The last application in the top right corner is an integration of the MVN BIOMECH system with a type of robotic application that seems a little bit different. This is the use of a powered prosthetic where the sensors are placed directly onto the prosthesis to measure how the prosthesis is moving along with the human body. All these types of applications are made possible with our MVN BIOMECH product.
In these 15 minutes, I'd like to tell you a little bit about the terrific opportunities for applying the technology developed by Xsens. And I'm going to show you some results that my research group at the University of Twente in the Netherlands has obtained within the project Sherpa. So I will briefly introduce the Sherpa project. It's a project funded by the European Community within the 7th Framework Program. And Sherpa is an acronym and it stands for Smart Collaboration Between Humans and Ground Aerial Robots for Improving Resting Activities in Alpine Environment. It is a big project with a consortium of 10 partners, among which there are 7 universities in Europe, 2 companies and 1 end user, the Alpine Italian Club, which is actually providing us with the problems that our robotic system has to be solved. So this Alpine Italian Club is a no-profit, no-political organization devoted to search and rescue operation in mountains and caves. It has 7,000 volunteers with more than 6,000 operations per year. So already when we were writing this project proposal, Xsens entered in the advisory board, and the University of Twente here in the Netherlands, the consortium created in Italy, University of Federico II indeed in Italy, and University of Bremen in Germany, we are using Xsens MVN BIOMECH. So just to give you a better idea on what the Sherpa project is about, I'm showing you this clip. So you see mountains, a winter scenario, you see flying vehicles, and here you see also a human rescuer close to whom there is a rover endowed with a robotic arm. So the goal of the Sherpa project is to develop a platform which is mixed, so ground robots and aerial robots, which should perform together with the human rescuer search and rescue activities in a real-world hostile environment, such as the one that I showed you in the clip. So we have a Sherpa team which is composed by different actors and they have heterogeneous capabilities. So the human rescue is very busy in the search and rescue activity, and he has higher cognitive capabilities. And then there are robots which are implementing autonomous behavior, but we want the whole system, so the robot and the human, to work together with advanced control and cognitive capabilities so that the rescuer is supporting and his awareness of the rescue scene is improved. Here at the University of Twente, besides developing the robotic arm that is mounted on the rover, we are focusing on human-robot interaction. And for that, we needed to select the proper technologies and also to develop bilateral teleoperation control. So what does it mean? As I said, the human operator is busy, and the robots have an autonomous behavior to support the human activity. By sketchy gestures, the human rescuer should should instruct the robots in order to properly tune and overrule the autonomous controller, and also the human rescuer should receive back information. And the information that the human receives back should not overwhelm him or her. So here, as I said, in Twente, we have developed a bilateral teleoperation scheme. We call it a supervisory control architecture. So if we are focusing on the bilateral teleoperation of a flying vehicle, we have the human rescue, we have a drone, so the flying vehicle that should scan a certain area, and we need to realize this communication, bilateral, so from the human to the drone and vice versa. So here in these blocks, you see the 7 blocks typical of any bilateral teleoperation. So from left to right, you see the human operator. Then there is the master device, which basically consists of a human-machine interface and its controller. And as we are seeing it, this master controller gives some information to the autonomous controller of the slave. And in this case, the slave is the drone, which you see in the right part of this block scheme. The slave might or might not interact with the environment, and the communication between the master and the slave is done through a proper communication channel. So I'm going to give you some details about the autonomous controller. And before that, I want to point out that for the human-machine interface part, we have selected the Xsens MVN BIOMECH for intention detection and gesture recognition, and I'm going to give you some more details now about while I'm entering in the details of the autonomous controller. So we have the master device on one side and the slave device on the other side. So the human interface is on the master side, of course, and through the task manager and the parameter handler, we are actually interpreting the signals that are coming from the human. So the task manager, for example, is interpreting the signals from the human-machine interface, so the Xsens suite, into tasks, like, for example, deciding about the target location. So XT here stays for the position that the flying vehicle should reach. Then there is this parameter handler here. This block interprets the operator's intention. So, for example, if we are assuming that the autonomous controller has safety distance, meaning a distance that the drone has to keep from obstacles, actually the human operator can influence the safety distance, because in the autonomous behavior the drone should play it safe, and so this safety distance might be big. But the human operator, since he or she has a higher cognitive capability, can overrule this safety distance and, for example, make it smaller. Then once safety distance and the final target position has been selected, there is this other block, which is the path planner. So we have a path generator and the path executor. And of course there will be a position control, a low-level control on the drone. And here in the bottom part of this figure here, there is the feedback generator. So the human operator will receive back some feedback in terms of haptic feedback and graphic feedback from the slave side back indeed to the operator. So for the path execution part, I want to show you the autonomous behavior of the system. So here we have, there is this red circle, we have the starting position of the drone, and here where there is this X, purple X, it's the target position. So the red lines are obstacles, and the blue shadows are the safety distance that the vehicle should keep from the obstacles. So when the algorithm starts, we select the target, which is indicated by recognition of the human gestures through the Xsens suite. And then once that target is selected, there is a path generation, and then the UAV will autonomously go towards the target. But the human operator can overrule the information about the safety distance. So we are using again the Xsens suite in order to change and maybe to reduce the safety distance. So before showing you the video of the experiment, I want to spend a few words about the complete software architecture. So there is a human operator, and the gestures of the human operator are read through input devices. So we are actually fusing different information from the Xsens suite and the MIO armband. And those technologies are running on a Windows PC, which is here. Then there is the slave device, and the autonomous controller is running on a Linux machine. And the communication in between those different Windows and Linux machines is happening through ROS nodes, so the robotic operative system. So the Xsens suite is publishing on the network information, so in the P channel with the frequency of 100 Hz. And those information are merged in order to realize, to influence and to overrule the autonomous controller once the operator decides that. And of course, we have a feedback, so we have some vibrotactile feedback, and we have a visual feedback. So I show you in this video, which is actually has been realized in our lab. So there is a human operator, there is a flying vehicle, and then there is there are two blue walls here, and there is a small opening. So the idea of this experiment is that the human operator will indicate a point behind the wall. But since this opening in between the two blue panels is too small, so it's below the safety distance, the flying vehicle will just stop in front of them. Then the human operator will overrule by bending his arm the autonomous controller. So basically the drone will be able to reach the set point behind this blue wall. So the activation is done by tapping the finger through the neo R-band, while the Xsens suit is used to select the set point behind the panel, and also the safety distance is increased and decreased by bending the lower arm of the human operator. So I will show you the movie now. So the operator taps his fingers to unlock, then he moves his hands to set a target. So you can see now that he taps the fingers, initial position, and then here it sets the new target. But the vehicle is just actually stopping because the opening is too small. Then the human operator bends the arm. The safety distance decreases, so that the vehicle is allowed to go through the opening. And then the human operator lowers the arms, the safety distance is increased. So here there is a top view. The blue circle is the safety distance. This is done in simulation. The safety distance decreases, and then behind the wall it increases again. So this is a bilateral teleoperation controller with a supervisory control done by the human operator and by using the Xsens suit. Another example is the teleoperation of the robotic arm that is going to be mounted on the rover. And so the control architecture is very similar to the one that I presented. So there is the human operator, there is an arm, and then the controller basically very similar. So I'll show you the 1 degrees of freedom case. So in this video, you see again the human operator wearing the Xsens suit, and there are EMG sensors as well to detect the muscle activity, and then there are vibrotactile actuators in order to give feedback to the human operator. So the architecture is very similar to the one that we have just seen. As an actuator system, so we are looking at 1 degrees of freedom robotic arm. It's a variable stiffness actuator system, so we are able to tune the output link, and that we are going to do by the motion detected of the human arm. And then by using the EMG signals, we are using this variable stiffness mechanism. So basically, we are trying to reproduce the human arm behavior into the 1 degrees of freedom arm. So here you see that the motion of the human arm are reproduced through the reading of the Xsens suit to the motion of the arm, of the robotic arm. While we are stiffening, also the system will be made stiffer, and so we are able to move higher weights.
Impressive.
This can be done thanks to the mechanical design of the variable stiffness actuators, which is able, by tuning the internal mechanical compliance, we are able to tune the internal stiffness. Okay, that brings to my conclusion. So for search and rescue missions, we have developed a bilateral teleoperation control architecture so that the higher cognitive capabilities of the human rescuer are reflected on both aerial platform, so the drone and 1 degrees of freedom arm. And the awareness of the human rescue improves because of the vibro-tactile feedback and of course the vision feedback without the human rescue and being overwhelmed. And so I must say that we are pretty happy of the technology, the human robot interaction technology made by Xsens, which is used to achieve the human-robot interaction and enhance actually human-robot interaction. And to conclude, of course, I want to acknowledge the founding agencies, so the European Commission and the Sherpa project. And thanks for attending this webinar.